So today we talk about motion perception. Perceiving motion. It's easy to do, right? You just kind of look and you see and things are moving and you can tell. So what we ask as psychologists studying perception is, how does the visual system process motion? You can see motion right now behind me, below me, whatever it is. And it's effortless, right? But we talked about how things that are effortless perceptually generally take a lot of computation. And motion perception isn't any different in that respect today. So motion after effects have been known for a long time. Aristotle mentioned them. He would stare at a waterfall, for example, and then stare the other way and see things instead of going down like the water. There was an after effect where things moved in the opposite direction. If you were a little kid and you used to spin around in circles and stop, and you'd see the room kind of moving in the opposite direction. Those are also motion after effects. Now we've got fancy computers, and we can have even fancier demonstrations of motion after effects. So your task here is just to follow the directions on the screen. So this doesn't take too long, and just keep your eyes centered at the little eye at the beginning, or at the middle of the screen. And what you're doing now is you're fatiguing motion receptors in your brain as we speak. And it's a pretty powerful display. It doesn't take too long. So probably right about now, you can look away, look at something else in the room, or look at your hand, and you will get the effects of the after effects of motion perception that Aristotle talked about. Ooh, I feel like I'm falling. They're temporary. And now look around the room and you will see, hopefully, the after effects that Aristotle saw, only not quite as, he didn't see them quite as dramatically as you did. So the question becomes, why do we have motion after effects? And does it tell us something about how we perceive movement? A lot of times we see perceptual illusions and, oh, that's really cool, or that's fun, or that's weird, or whatever. But typically, people study visual and auditory illusions to tell us something about how the perceptual system works. So what we know about motion after effects is that cells for opposite directions are compared for final output. So usually there's a balance of opposing cells that process motion in either direction. So for example, you have cells in the visual cortex that respond to upward motion, right? Now, there are also counterbalancing cells in the visual cortex that respond to downward motion. It's kind of like the opponent processes that we talked about with color vision. But if there's a nice balance, right? Because if things aren't moving, you want them to both be kind of equivalent. But if you fatigue them in a way that looks at motion in one direction continually, and then you look at something that's not moving, then there's this imbalance temporarily, and you perceive motion in the opposite direction, even though there's no motion there. So adaptation leads to a decrease in the output for the particular direction of motion that was fatigued or adapted. It may be due to cellular fatigue. It also may be due to a more active kind of calibration, such that, oh, well, this is kind of the new normal now. Things are always moving in this direction. Or it could be a combination of both. We know that we can tell that motion after effects occur not only in the eye, but particularly further up the visual chain. And we can do this. We know that the color after effects, right? So staring at this flag down below me here, and then you stare at a white background, and you get the red, white, and blue. But if you stare at it with one eye, and then you stare at the white background later with the other eye, you don't get any motion you don't get any color after effects. And so what that tells us is that the opponent process with respect to color occurs primarily in the retina. Motion after effects occur throughout the visual system. So for example, if you stared at that display with your right eye and then you stared around the room with just your left eye, you would get motion after effects. They wouldn't be nearly as strong, but they would work. All right, so motion perception theories. How do we develop a theory of how the brain processes motion? There are a few of them. There's corollary discharge theory, which we'll talk probably the most about, direct perception, and then a computational approach, which is applied in a sense, and how we're going to get robots to perceive motion, right? So if you have a decent motion theory perception, you need to explain these different cases, right? You need to explain when the retinal image moves and you perceive motion, right? So you're staring at a blank wall or you're staring out the window and a bird flies in front of you. The retinal image is moving and you perceive motion. But you also need to perceive the retinal image moving and there's no motion perceived, right? So if you're standing in your room by yourself and you turn this way, everything on your retina changes. The whole visual field moves, but you don't perceive any motion. Then you can have the retinal image be still and you can perceive motion. So this is more like the, it's over here, the bird flying, right? So you're tracking a bird or you're tracking a car or you're tracking something and it's staying in the same spot on your retina. Yet you perceive it as moving even though it's not moving across the retina. And then finally, where the retinal image is still, nothing's moving across the retina and no motion is perceived by you. This is the case where you're in your room and you're staring at the wall, nothing's moving and you don't perceive any motion. It's complex, right, to have one theory that's going to describe all those situations. Corollary discharge theory does that pretty well. And basically what it does is it incorporates the expected movement given input from the motor system, right? So if you move your head, there is input from the motor system that the corollary discharge theory can account for, right? So the brain here says, all right, we're going to move the eyes to the right and we're going to move the eye muscles, right? And so that information also goes to this neural comparison structure, right? That takes into account the movement that is being kind of directed by the brain and what's going on the retina. If the sensory signal is consistent with the expectation, then there's no motion perceived, right? So, oh, we're going to move our eyes or our head to the right. Everything on the retina should shift in the opposite direction. If that happens, then it's like it cancels it out. We've taken into account the expected change of the retina given what the motor system is doing. But if something is inconsistent with that, right? So if you move your head and then there's something that stays right there, then the system can detect that you're tracking something, right? Because that's not moving on the retina. That's an unexpected event given that you're moving your head, right? And so the unexpected stuff is perceived as motion. So corollary discharge theory can take care of these four different phenomena: when the retinal image moves and when the retinal image is still. Direct perception is a completely different approach, right? It's not as specific, but it essentially describes cues that viewers can use to perceive motion. So relative motion, surface, deletion, and accretion. So all this means is that when something moves in front of something else, it kind of disappears a little bit, and then it comes out the other side. So I'll see if I can do this with my hand. If I move my hand across my face, you're going to see the leading edge is covering up, and then all of a sudden I'm coming out on the other side. That process, the surface accretion, my face going away and then coming back, then the deletion and accretion are a cue to, well, maybe there's something moving in front of you, right? Changes in image size, right? When things get closer to you, they appear as though they're moving. When they get smaller on the retina, then they appear as though they're going away, they're moving. Motion parallax and motion from shadows. Motion parallax is just the idea that when you're moving, say you're driving in a car, right? And you look down at the lines on the road, down the middle of the highway, they're going by really, really fast, right? And maybe you look at the telephone poles a little bit further away and they're going by not quite as fast. And you look at the mountains and they barely look like they're even going past, right? So it's that's motion parallax, that relative change in how fast things appear to be passing you. And motion from shadows is essentially just the idea that when, you can there's a correlation between the object that is casting the shadow and the movement of the shadow, and we can get some information about movement from that. The computational approach is, again, very different from these other two approaches. So they're looking at it from a perspective of artificial intelligence, right? So how can we program a computer or a robot to detect motion in a way that's intelligent and in a way that is useful to the system. And so one of the kind of examples of this is something called the correspondence problem. So how does the system connect corresponding frames of vision? Now when I say frame, think in terms of film, right? Or in the more digital sense, but they still talk about frames. So what characteristics are important, right? So if you've got a stimulus that is, let's say, a hand right here, and in the next frame of film it moves this way. Well, how does the system know to correlate or to match up this particular point of the thing that's moving in frame 1 with the same spot in frame 2, right? Think in pixels if you want to. How do you know which pixels go with which in frame 1 versus frame 2? And apparent motion begins to answer the question. All right, what is apparent motion? Apparent motion is things that look like motion, but they're not really moving. And visual researchers have used apparent motion to study how the system processes visual motion. This dot looks like it's moving. It's not really moving. It's just a series of dots that appear and disappear. So what you're actually looking at in the PowerPoint presentation that I put together here is a bunch of dots. And one turns on. I was going to point at the screen, like you can see what I'm pointing at here. Maybe I can use this. All right. So this one turns on, and then it turns off. And the next one turns on and off and on and off. It's like marquee lights in Las Vegas. It's like anything that is your television, for example. Pixels are coming on and off, and it appears as though things are moving. Nothing is really moving, but apparent motion can be used to study real motion. And so when we think about the computational approach to vision and answer the question of the correspondence problem, what stimulus characteristics are important in correspondence? Shape or brightness. So we have two shapes here, right? We have a triangle and a circle, and the triangle is light in brightness and the circle is dark. All right, so let's see. Now we have a square, right? And all I want you to do as quickly as you can, when you see it move, say either left or right. You need to do it in your head because we're not in a classroom. But all right, so 1, 2, 3. All right. So when we do this in a classroom, what we have is about half of the class says right and half says left, right? Because the correspondence problem is what we're messing with here, right? So is it the case that motion is processed by the brightness or by the shape? And that is something that we can do experiments on and to help determine what's more important in particular situations, because the situation matters, right? So it's not just, oh well, it's shape or it's brightness. It can change, right? So here's another display of apparent motion, and I'll just play this here for you a little bit. And what most people see is the large circle going back and forth and moving from side to side of these smaller squares. But the question becomes, how do you see it moving, right? So when we have the circle that's here and it moves to the other side, do you see it swinging in and out, or do you see it swinging behind the circles, behind the squares rather? Some people even report that they see it kind of squeezing through, right? So the path of the apparent motion is subjective. And you can prime that, right? So if you show people displays that where something is always swinging back and forth, and then we show them this, right? Oops, this, they will perceive it to swing back and forth. If you show them, something squeezing through a small opening, then that information gets implemented into their perceptual processes in a top-down process. Previous experience and things that they have that they know to exist can influence incoming information or bottom-up information. So here's kind of an example of that, right? This is in top-down and bottom-up processes work together, right? So an illusion within an illusion. So what we're going to show you here is a blue triangle above a blue square. And I want you to just describe how they move. All right, what happened? Most people tend to report that, well, they both moved to the right, the square moved up and covered the triangle. Well, that's not really what happened at all, because if you look in my PowerPoint presentation here, you'll find that there is no square. I'm sorry, there's no triangle in this other display, right? It is, but you believe or you perceive that the triangle moved. All the triangle did was disappear, and the square moved to a place where you would assume the triangle to be, but it's actually not there. Top-down information. All right. The other thing I want to talk about, because we're going to be reading about this soon, is something called biological motion. It turns out that all the things that we know about motion perception get tweaked quite a bit when we talk about things that are biological that move. So, all right, what we're going to look at now is a demonstration of biological motion. The display to my right here is not moving right now, so it's not any kind of motion at all. But these series of dots, once they're set in motion, turn into the perception of someone who's walking, right? And it's the correlated movement of the parts of the biological organism that's in motion that we tap into. So we can tell that this is a person that's walking. And if we rotate them a little bit, we can tell that they've turned to the right and back straight and to the left. If we manipulate their walk a little bit, we can tell that it's more female or more male. We can manipulate how much they weigh. We can manipulate their nervousness, whether they're relaxed or whether they're a little bit more nervous. Even emotions such as happiness or sadness, right? So you know how somebody kind of walks when they're sad or when they're happy. And you don't need any of the other stuff to be able to get all of this from just a set of points that are moving in a correlated fashion. This is what's called point light biological motion. Point light because of the points of light. When this is all digitally done now, obviously, but when they first made the first point light walkers, what they would do is they had people in a black room, dressed all in black, and even with with a mask and everything, and they put ping pong balls where you see a dot, right? So the ping pong ball in the front of their head, one on each shoulder, one here, elbows, wrists, knees, hips, and they would film them doing stuff, right? And then when they played the video, they would turn the brightness down almost to nothing, so all you could see would be the white ping pong balls. You wouldn't be able to see the black dress against the black background. That's how they initially began to develop biological motion point light displays. And it turns out that you can tell when people are dancing or eating if you have point light motion with a dog or a seal or any other, or a bat or a bird. You can tell what it is. If someone's kicking a football, it's really, really easy to tell. We can tap into this correlation between the body parts, right? So when you're moving, your hands and your feet are moving in a coordinated manner, and we have an innate perception of that. So that's biological motion perception. Oh, so let's just make a male that is very light and very nervous, but he's happy. And maybe he's sad. I don't know. Maybe we're going to make it female instead. All right, you get the idea. You can play with this. It's biomotionlab.ca. All right, so that's a quick overview of biological motion perception, tacked on to the end of our general motion section discussion. Let me know if you have questions. I look forward to seeing you all on Wednesday.